So this lesson is about dual nature. A matter can behave both like a particle and like wave. Okay, so then de Broglie is the scientist. De Broglie is a scientist who found that the matter can behave both like a particle and like a wave. And he took Einstein's mass energy equation E is equal to mc square, and he took Planck's quantum theory E is equal to h mu. This is called Planck's quantum theory. Planck's quantum theory is based on wave nature, and mc square, E is equal to mc square, is based on particle nature. This is Einstein's theory and this is Planck's quantum theory, and he equated both the energies and he wrote mc square is equal to h mu, and instead of mu he wrote h into c by lambda. Mu itself is inversely proportional to wavelength. You all know that the wavelength is long, the frequency is less. So mu is equal to c by lambda, where c and c get cancelled. So lambda is equal to h by mc is the de Broglie wavelength, the wavelength associated with the particle. And so then this is a de Broglie wavelength h by mc in vacuum, because it has got the letter c, speed of light in vacuum. In the medium, it's lambda is equal to h by mv in the medium. And you understand that therefore lambda is inversely proportional to m. The de Broglie wavelength is inversely proportional to velocity. What does it mean? If the velocity is 0, the lambda tends to infinity. It's not possible. Such a case does not exist. So then therefore it has to be moving particle. It cannot be a static particle. It has to be compulsorily a moving particle. Next is this, where the mass is large, the de Broglie wavelength is negligible, so it can be ignored. So thus I don't carry a de Broglie wavelength because my mass is large. So de Broglie wavelength is only associated with subatomic particle whose mass is very negligible, subatomic. So therefore you understand that the de Broglie wavelength is associated only with a moving subatomic particle, and you know the reasons also. Okay, so then therefore larger bodies, when they are moving, will not produce de Broglie wavelength, only subatomic. What are the subatomic particles we know of? We know electron is a subatomic particle, a proton is a subatomic particle, the helium ion or a helium alpha particle is nothing but a helium ion, which is a subatomic particle. So these are all the smaller the particle, they're called subatomic particles, and so it will have significant de Broglie wavelength. Okay, so that's the introduction part of it. And so then the subatomic particle, let's take electron, let's study about emission of electrons. And so then in the emission of electrons could happen in 3 different ways. One is thermionic emission, next is field emission, then is photoelectric emission, which is called PEE. So this is the best way to emit an electron, because thermionic emission is based on heat produced. You have to supply heat to eject an electron. You have to supply a greater electric field in this case to supply to emit an electron, and you need a greater amount of heat and greater amount of electric field, and so the most preferred option is photoelectric emission. So how do they emit electron in a photoelectric emission phenomenon? They took a metal and they allowed an electromagnetic wave to fall on the metal. Then you know that a metal consists of free electrons in the outermost shell. These loose electrons, they get ejected, and so this phenomenon is known as photoelectric emission. The electromagnetic waves, what are these electromagnetic waves? You know, sunlight is also an electromagnetic wave, but I'll tell you, electromagnetic waves are those such as X-ray, gamma ray. Gamma ray is also radioactive. X-ray is used in medicine purpose. They take X-rays when your bone is cracked. Gamma rays are used in cancer treatment. Ultraviolet radiations, they pass in the swimming pool to kill the germs, and to purify the swimming pool they use UV radiations. Then microwaves, where in ovens you use microwave. Then you have radio waves. These are all infrared radiations, which is there in the TV remote. These are all the various electromagnetic waves that we know of: X-rays, gamma rays, UV rays, microwaves, radio waves, infrared waves. So one of these electromagnetic wave is chosen in such a way it's got sufficient energy. Whichever wave has got sufficient energy is made to fall on a metal surface, so that the electrons will get ejected. So that's about this phenomenon is known as photoelectric emission, and the electrons who are ejected is known as photoelectrons. So then how did they carry out this experiment? This is like a history of emission of electrons, where they tried to emit an electron using a zinc screen, in which they allowed the electromagnetic wave to pass, and they kept this in a gold leaf electroscope. Is this, which the whole apparatus is placed in. The whole apparatus is placed in vacuum. The moment they pass the electromagnetic radiation on the metal, both the gold leaf got repelled. The gold leaf, which was close together, now got repelled like this, which concluded that this is lost an electron, and therefore the metal has become positive ion. Therefore, these two have acquired positive charges, and hence they have got repelled. The repulsion of this indicates that the metal always becomes a positive ion, you know that, on losing an electron, and so then therefore electron would have got emitted. This phenomenon explains photoelectric emission. The next one is about it's about this experiment, where you take a quartz window in which there's an emitter plate and a collector plate. You allow electromagnetic radiation to fall on the emitter plate through the quartz window. So you have a quartz window, and this is a vacuum tube. Vacuum tube, you have a emitter plate, you have a collector plate. Okay, so then you connect the emitter to a negative terminal, collector to a positive terminal. What happens is, when the electromagnetic radiation is allowed to fall on the emitter plate, the electrons get ejected. But the ejected electrons have to go and flow like a current, milliamp current, then, which means you have to give this a positive voltage, and that's why we are connected it to a positive potential. As you keep on increasing the positive voltage, more and more electrons will move towards the collector plate and flow as milliammeter current, which is known as photoelectric current, PEC. Okay, for some positive potential, the photoelectric current will become maximum, and that's known as saturation current. Saturation current is the maximum current that can flow through for some maximum positive potential, beyond which, if you increase the potential, the photoelectric current cannot increase, because almost all electrons would have come to the collector plate. That's the first thing. The second thing is, now suddenly reverse the polarity. How do you reverse the polarity? Connect this to the negative and connect this to the positive. The moment you connect this to the negative, then all the electrons will start flowing backwards and reach the original plate, which means the photoelectric current keeps decreasing. The photoelectric current keeps on decreasing and becomes zero. The photoelectric current becomes zero at one point. Here it became maximum, which is known as saturation current. Here it's becoming zero for some negative potential V naught. And this is called stopping potential. Is that negative potential? Stopping potential is that negative potential at which the photoelectric current becomes zero. So these are the two things, that 1 and 2 points that you should write. I should draw this diagram. In fact, for a better diagram, look for the textbook diagram, where they would use a commutator. Just memorize the diagram in the textbook. And so that's about this, a simple diagram if you want. So now what they are doing is, they are doing a graphs. They are plotting a graph between photoelectric current and intensity. And the intensity I1 is less than I2 is less than I3, keeping frequency a constant. Very important. They notice that as the intensity is increasing, the photoelectric current is increasing linearly. This is the first graph. Okay, that's the third point you're going to write, apart from the first 2 points. The fourth graph is this graph, where it's a positive potential and there is a negative potential. You're giving positive potential, negative potential. Photoelectric current is plotted on the y-axis. The current is like this. For various intensity, you see the saturation current keeps on increasing. The saturation current, this is for intensity 1, this is for intensity 2, this is for intensity 3. And the photoelectric current also keeps increasing, but the negative potential, stopping potential, does not change. So therefore, your conclusion is, as intensity increases, I means intensity, okay, don't confuse with intensity increases, the photoelectric current increases, the saturation current also increases, but stopping potential does not change. Stopping potential does not change. Very, very important, doesn't change. The stopping potential is independent of intensity. Very important point. So the fifth graph is these are they keeping frequency a constant and changing the intensity in these two cases, first two graphs. Next graph is keeping frequency is changing, mu1 is less than mu2 is less than mu3, you're going on increasing the frequency, keeping intensity a constant. You're doing a graph between a photoelectric current and frequency, photoelectric current and stopping potential, where you get a graph like this, like this, and like this, which this is stopping potential 1, this is stopping potential 2, negative stopping potential 3 for increasing intensity, mu3, mu2, mu1. As the frequency is increasing, the stopping potential is going on increasing, but the saturation current remains the same. So therefore you understand saturation current is independent of frequency. The photoelectric current itself is independent of frequency. Only the stopping potential is dependent on frequency. This boils down to another graph, which is a graph between stopping potential and frequency, where it has to be a slope which is linear relationship, where this is known as threshold frequency mu naught. Frequency doesn't start with 0. It starts with a threshold frequency. This is for a metal A and this is for a metal B. And this is a threshold frequency for A, this is a threshold frequency for B, and you extend this y-axis and join this on the y-axis. You know, V is equal to W by Q, so it's minus W by Q or W by E, where you write it as W naught, which is called the work function. I'll come to that point later. So thus you have it for a metal B and a metal A like this. Okay, so this is about the graph, and you notice that the slope is the same. Slope of the metal A is equal to slope of the metal B. It doesn't change. Okay, so these are the various graphs that you should draw in the conclusions of this experiment. For this diagram alone, you can verify the textbook for the diagram. So this is the first experiment and its observation. Now Einstein is trying to give an explanation, theoretical explanation for these graphs. Theoretical explanation for these graphs. So he is looking at this graph and saying, why do an experiment with vacuum tube? Why it's not even necessary? I will explain the outcome of these graphs by means of theory, by using Planck's quantum theory. Which is wave nature. Quantum theory, which means it's wave nature. The matter is wave nature. Okay, where according to Planck's quantum theory, energy is equal to h mu. That means the matter is made up of, the light is made up of packets of energy. Light is made up of packets of energy known as photons. Using this phenomenon, he is going to explain the graph. So Einstein used Planck's quantum theory, which means light is made up of pockets of energy known as photons. According to wave theory, it's not particle, it's photons. Okay. So then when electromagnetic radiation is going to fall on a metal, every photon is going to interact with an electron and eject an electron. So, and the more the number of photons, the more electrons will get emitted. Okay. So actually speaking, he defines intensity. He defines intensity to be number of photons crossing unit area per unit time. Okay, so number of photons crossing unit area is the main point. So as intensity increases, number of photons increases. As number of photons increases, the photon electron interaction in the metal increases, which results in a large release of electron, which constitute the photoelectric current. The photoelectric current, the release of more number of electrons are moving, photoelectric current will be more. So this explains why there's a linear graph between PEC and intensity. He explains it by definition. The intensity is, according to him, is defining intensity as number of photons. And the more the intensity, more is the number of photons. More is the number of photons, photon-electron interaction is more, and hence photoelectric current increases linearly, and that explains the first point. The second point, he is talking about work function. Okay, he says that, okay, the work function is actually, every metal has its own work function. Okay, work function is the energy required to eject an electron from a metal surface. What amount of energy is required to eject an electron? It's represented by W naught or a phi naught, which is also H into mu naught, where mu naught is the minimum threshold frequency. I told you in the graph, it will be mu naught, where it's cutting, it is never at zero. You need a minimum energy which is known as threshold frequency. So this is known as work function. Its SI unit is in electron volt. Electron volt to joule means you have to multiply it with 1.6 in 10 to the power minus 19. Joule to electron volt means you divide the joule value by 1.6 in 10 to the power minus 19. You can convert into electron volt. These are the conversions, but this lesson necessarily needs SI units in terms of electron volt, not in terms of joules. So this is the work function, which is the minimum energy required by the electron. Minimum energy required by metal, for a metal to eject an electron from its surface. Okay, the best example that I would say, sorry to be really funny. So imagine your face is here, your mouth is here, your teeth, you want to take away teeth. Teeth is an electron and your mouth is the metal surface. Give a slap. Just slap your face. Will the teeth fall? No. It should have sufficient energy to allow the teeth to fall. So the incident wave should have so much energy to allow the electron to eject from that. Energy required is called work function. Okay, but now Einstein is going to elaborate more on this. He says the incident wave should have an energy which is sufficient enough not only to remove the teeth from your mouth, but also to accelerate the teeth and make it fall on some other place. So that much energy. So then like that, the incident wave should have an energy h mu which is sufficient enough to eject an electron, which is the work function, which is the energy phi naught or a h mu naught, or also provide it with an acceleration that is going to move with the velocity half mv square. So it should have that much energy h mu which is sufficient enough to eject an electron, which is h mu naught, which is the work function, plus also half mv square to accelerate the electron with a maximum energy. So this half mv max square, velocity maximum the whole square, is equal to h mu minus h mu naught. He said that this kinetic energy is a physical quantity which can never be negative. Never be negative. Therefore, he concludes that the mu has to be greater than mu naught. In this, h is a Planck's constant, which is 6.6 × 10 to the power minus 34 joules second. Okay, so then therefore mu has to be that the incident radiation should have a frequency greater than the threshold frequency for the photoelectric effect to occur or photoelectric current to flow through. So thus he concludes this using this mathematical expression. So these were all explained by Einstein. The third point, which is a very, very important point, why does the stopping potential does not change even though the intensity is changing? Because stopping potential, when you multiply with the charge, becomes energy. The energy required to stop the maximum movement of an electron, the flow of electron. Therefore, you can replace this equation half mv max square as h mu minus h mu naught also to be ev naught is equal to h mu minus h mu naught, because the maximum energy with which the electron is moving can also be the maximum potential which you are giving to stop the movement. So from this he is saying, since ev naught is the substitute of energy, only the frequency will affect. The frequency is increasing, it will affect the stopping potential. You know that the frequency was the stopping potential graph. As the frequency kept changing, the stopping potential also kept increasingly negative. But the intensity is simply the number of photons. Will only cause more electrons to eject. But doesn't mean that the energy is going to increase. Intensity would not contribute to any energy increase. Therefore, intensity will not contribute to any change in the stopping potential. Okay, that beautifully explains the entire graph. And then he also says the last point, where he says when the electromagnetic radiations falls on a metal surface, it ejects the electrons and it's almost instantaneous process. Instantaneous. That is, it occurs within 10 to the power minus 9 seconds. So it means there is a bulk absorption happening. Bulk absorption phenomenon that is happening. Instantly it's absorbing and emitting the electrons. The photons get absorbed. So bulk absorption of energy is happening. So we were thinking that it will be a continuous absorption. A continuous absorption, but on the contrary, this results in a photoelectric effect occurs with bulk absorption. So that these are the observations done by Einstein, and you should write all this when they ask you to explain photoelectric effect by Einstein in terms of Planck's quantum theory. Then he did a graph. This graph is beautiful. You know E V naught is equal to h mu minus h mu naught. From that you write h by E, take the V naught to the other side, plus this is work function by E. And so then this is like y is equal to mx plus c. In the place of x you have frequency, in the place of y you have V naught, and you know the graph between stopping potential and frequency is a slope like this for a metal A, and this is a slope like this for a metal B, I already told you. And where it is cutting y-axis is this intercept C. And can you see it's minus, it's minus. It's like y is equal to mx plus c, where c is negative, minus phi naught by E. Minus phi naught by E, which is for a metal A and for a metal B respectively. So this is the graph, and so you understand that the slope, no wonder the slope of metal A and metal B are the same, because slope's value is h by E. H is a Planck's constant, E is the charge, H is a Planck's constant. So it's never going to change. H by E is a fixed value. Okay, so then that's about it. And then you can also do a graph between half m V max square is equal to h mu minus h mu naught, where you take the 2 to the other side, where you cut and bring the m to this side. So you get V max square, velocity square, 2 h mu by m minus 2 phi naught by m. You know, you can h mu naught can be written as phi naught, which is the work function. W naught also you can write. So then therefore you're going to plot a graph between V max square and frequency. The slope is the same, but the slope's value here is like this is y is equal to mx plus c format, where x is nothing but frequency. So m is 2h by m. In this, the slope is the same, but the value of the slope, m here stands for slope. Slope is 2h by m. M is the mass of the electron, h is the Planck's constant. Whereas here the slope is h by e. If you plot a graph between V naught and frequency, whereas here it's V max square, and what will be the y-intercept? In this case, it's 2 phi naught by m minus 2 phi naught by m for metal A and metal B. That clarity you should have. Because they'll always ask you this question in the board exam. They will give you a graph like this, where they will say this is a graph between V max square and frequency, where one of the board exam had this sum, where the x-intercept is n and the y-intercept is L. You know from this what is tan theta, you write what is tan theta, which is L by n, which is a slope. But the slope in general for V max square versus frequency is 2h by m, we just learnt it. So you write 2h by m is equal to L by n. So write what is h from this, L m by 2n, and thus you are able to arrive Planck's constant using L and n given in the graph. They'll also ask you what is the threshold frequency. This is the point, and this point is at a distance n from the origin. Therefore, threshold frequency itself is n. So such a question came for board exam, where if you fail to notice that tan theta is also slope and you write L by n, you cannot do this sum. And you should understand this is 2h by m and not h by e. If the graph was between V naught and frequency, it is h by e. Okay, so that's about this sum. And there are many other numericals which I'm going to continue now in this video. Before which I'll just do one last thing. This derivation is very, very important. From de Broglie's hypothesis, from de Broglie's hypothesis, you're going to arrive at Bohr's postulate. Okay, so then you have an electron which is revolving around the hydrogen atom, nucleus, hydrogen nucleus. You know that the moving subatomic particle, when it's revolving, will produce wave de Broglie wavelength. So 2 pi r will have n lambda, it may have n number of waves, depending on the octet, we don't know. So then you write lambda as, according to de Broglie, is n into h by 2 pi. And lambda is h by mv, sorry, lambda is h by mv according to this lesson. Planck's lambda de Broglie with h by mv. Take the mvr to the other side. Right, nh by 2 pi to the other side. This is angular momentum, which is nh by 2 pi. Thus, we arrived at a Bohr's postulate from taking de Broglie's. You arrived at Bohr's. Very, very important. After this is the numerical. Okay. After this is the numerical. Before we start the numericals, I would like you all to memorize certain things. Okay, such as